well, it also uses some very interesting. I strongly recommend you to read this paper. It's in the references, and I'll upload the presentation too. It uses some heuristic principles of induction, which are probably going to be interesting to investigate more. And it combines two well-known, effective genetic programming approaches, generation-based and elitist incremental evolution. Incremental evolution means you don't just discard the population, right? You continue evolving it. It's kind of like human society. So it goes on and on. And we retain all the crappy parts as well as the good parts, but that variety is something that gives the human society its incredible fitness. So the same approach can work with machine learning as well. And well, generation-based is kind of like the human society. There are generation X, generation Y, generation I don't know. And then the elitist incremental evolution makes sure, well, I suppose the richest guy always gets the girl, something like that. So it means you want to keep evolving the best fit. And this approach allows for a good deal of variation, so it's good GP, and we will still get to keep the best solutions. It's a good combination, I think. And well, let me expand the generation-based learning here a little. We first populate programs by sampling from the PPT structure, and then we evaluate them, of course. This is standard, right? And then we are learning from programs, and there is an algorithm that makes the best program more probable. So we're changing our structures, and fitness-dependent learning is an interesting, one of the interesting heuristics they use. The fitter programs get more bound, they get even more probable. And PPT mutations are in the next step, and that's going to help us not just try to improve the best individual or the best PPT, but it will let the larger programs evolve faster. And this is supposedly, okay, well, this is the number of guys and in the probability vector at each node. And this is just a constant. And this is the number of nodes in a tree. And so that's interesting because with this probability, we are mutating a program. So it's variant, and they found this works well. Okay, well, let's move on to ordered optimal problem solver. This is one of my favorite algorithms in the induction field. It's an incremental generalized Levin search, or also known as adaptive Levin search. And the transfer they showed in the paper was, I think at the time, extremely impressive. It's transferred information from an abstract language problem, a regular language problem. Was it? Okay, well, a language problem, to towers of Hanoi. So this is not exactly induction, but if you can, of course, apply this to induction. And they got a real nice speed up compared to solving the towers of Hanoi problem on its own. They got this 1,000 times speed up. We showed there might be something remarkable about these incremental learning approaches. And this paper uses a probability vector coding of program instructions. So each instruction has a probability. We just multiply them and get the probability of the program. And that probability vector is going to be our basically probability mass functional programs, right? Okay, so some OOPS features. It's got, well, the implementation is really good. You should probably check out the details. It's got a nice stack tracking search implementation. It's a very nice Levin search implementation, as a matter of fact. It's one of the best out there. And it uses Forth as a reference machine. And rationale behind this is Forth programs do tend to be very short. And since the universal search is very costly with increasing program length, this is important, of course. And algorithm proceeds as follows. We divide the whole search time into two halves. In one half, we search programs from scratch, from zero. And in the other half, we try to extend the last good program. So this is almost bias optimal, I think Schmidt-Huber writes in the paper. Okay, so well, what is the update method in OOPS? OOPS is actually very interesting in this regard. There are some differences between the conference and journal paper, but I suggest you to take a look at them both. I think. And well, you can also download the source code and take a look at it. I think that's going to be a lot of fun. And maybe, who knows, with today's machines, maybe it will just be using level AI. So I didn't try it, so you should, okay? And there's a special bump instruction, there was, as far as I can tell, that promotes the probability of an instruction. It bumps its probability up, and of course, renormalizes the whole PDF, so the others go down. And OOPS performs dynamical updates throughout search. The probability density functions changes, dynamically adapts throughout the search. And we can also conceive, of course, of all kinds of instructions, instructions and subroutines that will modify probabilities, call previous solutions, programs found, and edit them also. So it's actually a fairly complete solution for Forth. And I don't know how far this has been extended, but I think there might be interesting experiments to be made here. And since this was shown to work effectively in practice, it might be worth the time to try to make more experiments to verify that it actually works with long training sequences, which means we have many kinds of problems in sequence, not just 2 or 3. All right, so all right, let's come to some of my own work. Solomonov suggested that I continue with the stochastic grammar approach. At first, I was a bit skeptical. I didn't quite see how it would work. It didn't seem to me that it would have much of an impact, to be honest. And I didn't have a good algorithm in the beginning, for sure. But we can, with some effort, we can obtain efficient update algorithms, that fast update algorithms that update the grammar and grow the grammar without ruining the whole program search logic. And these update algorithms work synergistically, which means they work together well. They don't get in the way of each other, at least. Okay, and so the nice thing is this is exactly bias optimal, where it's just a normal Levin search, but it has incremental learning feature. And well, I call that memory design approach heuristic algorithmic memory, because we're recalling invented heuristic programs and we're storing them as programs. That's right. We're remembering them algorithmically. And guiding probability distribution is the long-term memory of the system. And stochastic grammar just gives us a priori probabilities since we have maximum ignorance about the programs we produce. We just multiply production probabilities. We don't really consider the dependencies among them. And most of these program probability models are like that. I'm just trying to give you an idea of how to do this. And this is also the case in DeFalco's 2006 paper, where he used genetic programming to approximate universal induction and solve some interesting regression problems with this approach. And if you also have some fast algorithms to update this heuristic algorithmic memory, it works pretty well. Oh. Okay, so the last version of this thing was using a stochastic context-sensitive grammar, which I thought would be useful for representing some realistic programming languages. Or it can definitely represent Lisp and my favorite meta language ML. And each production here is a probability, so stochastic grammar is just grammar as usual, but we are assigning a probability to each sentence in the language. And well, you know, I suppose you all know the language here, so I'll be quick. But productions are of this form. This is non-terminal, right? And we're replacing this guy with this prefix and with this suffix with gamma here, right? So that's the transformations that are allowed in this grammar. And we just give each of these guys a probability here that we write here. And then we again just, to obtain the probability of a sentence in the language, we just multiply the probabilities. And so let's not complicate it too much because these search algorithms are complex, right? So we're just keeping it simple too. Okay, so, well again, transfer learning, we have just a bit of formalization, nothing too serious is going on here, I assure you. It's, we have a training sequence, a set of data points, right? So these could be case claim, these could be bit strings, right? And we're going to obtain a set of solutions for the solution of each problem here. We have n problems. And each problem here, excuse me, each solution SI here, that's part of the solution corpuses, is also a set of programs. Sij, I notated it because induction means, due to diversity principle, is going to give us not just one model, but a set of models if we do it right. Okay, and that's because each solution does need to have multiple models. And then looking at all the previous grammars that correspond to the each problem, we're going to get from the last grammar and all the previous history of grammars to the next grammar. So that's the general update problem here. So well, if we design better algorithms to do this, hopefully our total search time is going to decrease. Okay, so this is not much of an important thing, but instead of a derivation tree with the context-sensitive grammar, you use you can use a derivation lattice, which is a bit more complicated, basically the same thing. And the update algorithm here, as the input, uses the solution corpus, which is all the solution programs we obtained so far. And we also have the derivation of each program, so we know how they were generated, right? And we have the operator properties and formal parameters and whatever else the language requires. And the update algorithm of Terra machine preserves the universality of the grammar, so it's example bias optimal. And we can also sort the whole history of grammars and try to exploit that. And let me be a bit quick about this. We're again modifying probabilities. And it's basically the same thing, but what we're doing is we're combining the production probabilities in the solution corpus and the original grammar of the reference machine. And this makes sure that while you don't lose the universality of grammar, you can still bump the probabilities you need. And the second algorithm was memoization of solutions, which means storing all the solutions in the grammar where it belongs. So in a Lisp-like language, you can have these additional this additional non-terminal, which will probabilistically expand to all the previous solutions. So this corresponds to the calling previous programs instruction in OOPS, right? So it's just we're just extending that from the probability vector thing to the stochastic grammar thing. Okay, so that's also sort of straightforward. And, then we had this mostly new algorithm. I think similar approaches have been tried. So we actually have a lot of transfer learning algorithms in neural network community that uses stuff like frequent subgraphs. So this is the same idea. I call it derivation compression because once you find the frequent patterns in the solution corpus, this might dramatically compress the whole derivation information, right? So that's what we're trying to do here. And the better we compress, the more we have learned about the solution corpus. What we're really doing is, I'm not going to show that, but we're trying to extrapolate from the solution corpus. So we're actually solving a set induction problem over the solution corpus. So this uses another induction approximation to solve the memory problem. Okay, so yeah. So we have a set induction model to decide which productions it can forget to, and all right. So let's move over to incremental learning with RNNs. So we have a better picture of what's going on. Transfer learning in a deep neural network model. I don't know. Maybe it was Chan 16, and well, this famous algorithm, net-to-net, right? You probably heard it. So, but this applies to deep neural networks, which I think basically means multi-layer feed-forwardness with a lot of hidden layers nowadays, right? So, but with some special layers like convolutional neural networks and did something yesterday. So there are a lot of variations, but you all know the basic theme. This algorithm, how to transfer the solutions from previous training epochs. We introduce some new data and we want to retrain instead of training the neural network from scratch, with backpropagation or what have you. And this net-to-net widens a layer by adding more neurons to it, or adds some redundant layers to allow the learning algorithm to grow its entropy to connect the knowledge, the information from previous training to the new data points. And the trick is we use function preserving maps, and some important cases are covered in this paper, but the general problems seem kind of open, so this probably is something very interesting for anyone interested in neural networks nowadays. And here's the stuff from the paper. So this is an example of the function preserving map, right? So they added a new neuron here, but they divided the weights. So it's the same function, but we got more structure here. So when you continue training, hopefully the weights will adjust and we will have achieved transfer learning. And the deepening algorithm, that's the horrible image, I'm sorry, but this is the original model, and these are layers that are initialized as identity mapping, so we don't really want to change the function while we're adding stuff to the neural network. We're trying to, what are we trying to do here? We're trying to grow the network, right? So this will allow room for learning, like more memory. Basically, that's it. So the basic idea is quite simple here. But the means to achieve this, to find this identity mapping might not always be possible for every layer. So they identified which layers you can easily manipulate like that. But the general problems seem kind of open. You can do research on that. And but the great thing about this, like most neural network approaches, these are very fast and practical algorithms. So you can easily deploy them in your systems. And okay, well, let's get to this new transfer learning approach for reinforcement learning. This algorithm is called general reuse of static modules. I don't know if I'm pronouncing it gruesome or okay. Gruesome. Oh my God, gruesome. That's horrible. It's funny though, right? So Raylan and others published also this year, I think.